Hey everyone. So, today is going to be a pretty easy day for you guys. Yesterday, we talked about how to use a balanced reaction to do the stoichiometry. So, how do you do stoichiometry? Um, Basically, we have a number of moles of one thing in this balanced reaction, and we can use these coefficients to figure out how many moles of another thing we have. It's pretty straightforward, but you guys need some practice. So, what are we going to do with that? So, I've printed out a sheet of problems for you guys. Um, just with a certain number of moles of one thing. Here's the balanced equation. You go do the stoichiometry. So I'm going to let you guys know all of these reactions are going to be balanced already. You won't have to do that yourself. All you'll have to do is show me your work. So just go through, show your work, and do these 25 problems. Since we just talked about it yesterday, and I know that Teams meetings may not be the best way to learn a skill, I'm going to go through and do a few of these problems myself in this video to show you. If you feel like you're good, just dive right on in and get that done. If you need to, if you want to review a little bit, here's your chance. All right, so let's see here. What do we got? We have ourselves a balanced reaction here. Looks like iron oxide plus carbon goes to iron and CO2. So this looks like it is a single replacement reaction. And it wants to know if we start out with 1.5212 moles of this iron oxide, then how many moles of CO2 will be produced? This is going to be pretty useful because we know CO2 is a gas while this iron is a solid. It'd be nice to know, like if you were a chemical engineer or something, it would be good to know how much gas it is you are producing, because if you say this is in a sealed container, if it's too much gas, it's going to explode. So this is something that you're going to need to know. All right, so let's go through and do this again. What I like to do is think about where we're going. How many moles of CO2 do you have? So CO2 is what we're after, and we're looking for moles of CO2. And one thing we know is the balanced equation and 1.5212 moles of iron oxide. What is this? This looks like iron 3 oxide. All right, so how are we going to convert this thing? Well, I need to get rid of the iron oxide, and I need to pick up CO2. All right. So now, if I look at my units, I know I'm going to have moles of CO2. Now I just need to figure out what are these numbers. And remember, we get these numbers from the balanced equation. For every 2 iron oxide that go into this reaction, I'm going to get 3 CO2s out of the reaction. And now that I have this set up, I can check my units. Yes, moles of CO2. And I'm trying to get to moles of CO2. I'm good. Let us do the plugging and chugging. So 1.5212 times 3 divided by 2. All right, and so we know we're going to have 2.2818 moles of CO2. And that's that. Done. Check mark. All right, next one. Here's some cadmium and copper nitrate. Looks like copper 2 nitrate is going to become cadmium 2 nitrate, and copper. Again, another single replacement reaction. Things like this can be useful for things like batteries. Single replacement reactions like this can be used for batteries or copper plating. Like since we're making solid copper, if you are going to be plating something with copper, this is one way of doing it. You guys kind of saw a little bit of that whenever we were doing the single replacement reactions, where we had a piece of metal kind of turn kind of brown. That's, copper plating. Congratulations. Again, okay, so we want to know if it's 4.7 blah, 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 blah moles of copper are produced. So we know how much copper is produced. I want to know how many moles of copper nitrate need to be reacted. All right. Now, I don't even need to I'm not even going to write out anything here, because this balanced equation is 1 to 1 to 1 to 1. Everything here is in the 1-to-1 ratio. So if I have 4.7 blah, blah, blah moles of copper, I know that I'm going to have 4.7518 moles of copper nitrate reacted, because everything is in a 1-to-1 to 1 ratio. There's that. Now, can you do what I just did? No. I want you to go through, even if it is a 1-to-1 ratio, to actually go through and show your work. So, copper nitrate. On this side, 4.7518 moles of copper. And copper's on bottom. Copper nitrate is on top. And it's a 1-to-1. So copper is crossed out. So it's 4.7518 moles of copper nitrate. So yeah, even if it is a 1-to-1 ratio and you know that it's going to be exactly the same, still go through and write out your process. It is always a good idea to show that you know what you're talking about. It's pretty easy for someone to call you out and say, you don't know what you're talking about. It's like, no. Evidence. Here's the truth of it. All right, this one we can see is we want to have copper oxide. How many moles of carbon will also be reacted? So this is going to be kind of a 2-to-1, or I guess in this case 1-to-2 ratio going on. So again, we can kind of show this. Moles of carbon. We have 1.4895 moles of copper oxide. What is our thing going to be? We need to drop the copper oxide, pick up the carbon, and it is a 1-to-2. 1 carbon for every 2 copper oxides. So then we just need to divide this by 2. And this is going to turn out to be about 0.74 435, somewhere in there, if I did my math correctly. Again, I'm fairly certain that's right, but no, I was wrong. It's not 3, it's 7. This is why you should always go through and actually put your work down and do it, because you might be wrong. All right. So this is an example of what I want. I have a PDF. Do these problems. It's exactly looks like this, just different numbers and different reactions. So go through and do this, submit it, and you're done for the day. On Thursday, we're going to be talking about grams. going from grams to moles first. So that's going to be going on Thursday. Okay. And then on Friday, you can imagine probably another assignment like this. All right. Have a good one, guys. I will see you guys on Thursday.